Today we'll be looking at problem 4, median of two sorted arrays. As per usual, the 3 steps of solving any problem are 1, understand, 2, visualize, and 3, implement. So, given two sorted arrays, nums1 and nums2 of size m and n respectively, return the median of the two sorted arrays. The overall runtime complexity should be O log m plus n. Look at the first example, nums1 is 1, 3, nums2 is 2. If you were to somehow sort the array of the merged here's the merged array. If you're somehow to sort them, you would see that the middle number is 2, so the median is 2. Example 2, we have 1, 2, and 3, 4. If you were to merge them together, it would look like 1, 2, 3, 4. In an even numbered array, you would take the two middlemost numbers, 2 and 3, add them together and divide it by 2, so this is called the average, and you get 2.5. Look at the constraints. nums1 length is m, nums2 length is n. M and n are between 0 and 1,000. M plus n is between 1 and 2,000. And each number is between negative 106 and 106. So no surprises with the constraints there. So the first thing to think about is the fact that the time complexity should be O log m plus n. So we can't just sort, like force merge the two arrays and then apply a sorting algorithm, because best case scenario will be, n log n time is just going to be too slow. So what do we know about the array that can get us to the solution in, m plus n time? So we'll just take our first example, 1, 3, and 2, and we're trying to get to 1, 2, 3 and find that guy. So we need to find that 2. So here's the question. Ready? Imagine we're just looking at the rightmost numbers. Which is bigger, 3 or 2? Okay, so it's 2. It's 3, right? So 3. And let's move this guy down back 1, because we've already looked at it. What's bigger between 1 and 2? The answer is 2. And here's a different question. How regardless of the numbers, how big is the the merged array? Well, you can just look at the length of the first array, which is 2, length of the second array, and it's 3. Length of merged array is 3. And here's the question. At what point, what index value is the median? So median's index value is 1. So we know that. So all we have to do is, so what do we do? Let's do that one more time. So we look at the rightmost numbers, we compare the largest number, and we see that it's 3. We put it into this array and move this guy back 1, and then we compare the 2 and 1. 2 is bigger, and then we realize that we're already at the index spot of the median's index value, and at this point we can just stop iterating, because we've gone far enough. We could keep going, but for saving time, we can just stop right now. And that's really all there is to this algorithm, just doing exactly that. Just keep comparing the largest values until you've reached the median's index value, and at that point stop. If 2 more pieces of theory though, like this problem is usually called a 2 heap, and the reason for that is that the process of comparing the largest number is like a form of heap where you just have so what is a heap? So a heap is you have like all these numbers. Let's say all these numbers, and then you kind of like without necessarily sorting them, you can in a pretty fast way, you can just push the largest number, in the case of a max heap, to the top. So if let's say you had a 30 down here, you could a max heap process could get you that 30 up here to the top. In the case of a min heap, let's say there was a 1 here, it would bring you to the top. And it sounds like unrelated to whatever the heck we just did, but the reason it actually is related is that, you have, very small heaps, 1, 2, and in this case, actually 2 would go to 1. And because it's so simple, we don't actually have to write, a heapification algorithm. We can just compare the two numbers. But there are other types of two heap problems where, like, you will have to deal with, like, a number of values in your heap, and then you want to do a proper heapification algorithm. But in this case, you don't have to write a heapification algorithm. You have to compare the two numbers, and so that covers the heap, the max heap bit. And then the reason that it's called the two heap is because, in fact, looking at, like, imagine you put, like, the resulting array of the largest numbers. In fact, a heap algorithm would then pull the 2 all the way to the top, and it would look like that. And we don't necessarily need to do that, because we can just look at the final number in the array to know which is the smallest number. But there are other types of problems where there'll be more numbers that you'll have to, like, do a proper heapification for, and this isn't one of those. But you start to get, like, the sense of the heap in both, like the comparing for the largest number and then getting the final median number. You have the max heap for finding the largest, and then min heap for finding the median value. And the final concept to think about is that, it's kind of like a 2-pointer, where you have 1 point for the first array, 1 point for the second array. And let's just make this bigger so you can imagine. So we're kind of just starting our pointers at the biggest numbers, and we're just iterating these guys backwards as we compare and decide who is the biggest guy, and we push to our array. So with that said, let's implement exactly what we just said. What can we say first? We want the length of the array, the total size. What else do we need? We need the median index value. Median index equals, so we can say math.ceil total size divided by 2. So, you may be wondering, like, okay, so imagine, like, the number 3 divided by 2 is 1.5. Like, so you're probably asking, like, why aren't we doing this math floor? Why are we doing this math ceil, which would actually bring us up to 2? And the reason for that is that because we're starting from the right, like, this actually can become one indexed, where okay, let's do exactly that. 1, 3, and I can just write it here. So what we're doing is that we're going to be iterating from this point, but we're going to treat this as the length of the array. So it's 3, and then 3 is greater or equals to 2, and that'll only move our iterator back 1. So that's why, and maybe it's like bad practice to call it median index, so I'll just call this median point. But that's the reason that we want to do ceil instead of floor. You can definitely do floor, but it'll make you do a couple extra steps to find that median value, and this is just slightly more efficient. So forgetting about the tangent, what do we need? We need to set up our pointers, our 2 pointers. So I'll call it nums1 pointer, nums1 the length -1, cons nums2 pointer, nums2 the length -1. We want to be comparing the two values. So we had our 3 and 2. How do we get even know about those numbers and their existence? It's nums1 pointer. So it looks like we're getting ready to start comparing. At this, what did I misspell? Nums2 pointer. Okay, so imagine for a second, you actually like an array is empty and we only have, you know, this array here. Like we need to be prepared for that. Prepared for that. So if here it should be, let's just call this 1 equals this, 2 equals that, and then we can say we want to make sure that our pointers actually exist, that it's not you know, a negative value. And you know, in the case that, oh sorry, that it's yeah, just that it doesn't though yeah, we have a value, because you know, it could be 0 minus 1, which is -1. So in this case we want to do infinity if it's if we don't have that pointer, and the reason for that is that we don't want that number to ever win. So you know, if you want to be comparing one, like 3 against, you know, this empty array, like, you know, 3 should always win. Like we don't want, you know, this non-existing number to ever win in the comparison of what's larger. So let's just make these guys infinity if the pointer is missing. Okay, so we have our total size, we have our median point, we actually have everything we need. Now we need to just start doing our comparisons and then return our median. So let's start iterating for let say I equals total size, I is greater or equals to our median point, minus. So that'll get us to our final destination. And now we just compare the two values. If 1 is greater than 2, that means that, oh, and then const max array. So let's push this guy, push 1, and then we can move his pointer back 1. And what else can we do? We can, oh, and let's call these, make these guys lets. And then 1 equals, oh, we actually want to just copy this exact same thing, else, and you know, just the exact opposite. Push 2 nums to pointer, 2 nums to pointer, nums to pointer. So that's the whole comparison process. Now we need to just find the median. So definitely remember, we have either an even numbered array or an odd numbered one, and we handle them differently. So if total size mod 2 equals 0, that means that it's even numbered. What do? We return, we can just, so pop in JavaScript is where you take the last element in the array. So remember, we have 3 and 2. Okay, so let's say I actually look like 4, 3, 2. We return this plus, you know, the next, so it'll be, in that case, the first pop will be this guy. Then we pop this next guy, so those are the two, you know, middlemost numbers, and we divide it by 2. So that handles this case. Otherwise, we just need to return the furthest most number in the array, and that should do the trick. Let's see how we did. And where did I mess up? Little question marks to make a proper ternary form. Oh, we also missed these guys. Okay, example cases submitted. So there you have it, and yeah, thank you. Catch you later.